Welcome back to the episode 5.18 of our video course Parallel Programming and Optimization with Intel Xeon Phi coprocessors. In this episode, we will cover load balancing in heterogeneous systems. In some cases, Intel Xeon Phi coprocessors can be used in tandem with Intel Xeon processors. Indeed, as we saw throughout this course, code optimized for Xeon works well on Xeon Phi and vice versa. So when a system with a powerful Xeon and one or several Xeon Phi coprocessors is available, it may make sense to use all of those computational resources. The result will be a symmetric heterogeneous calculation. It is called symmetric in the sense that both architectures will be using the same code, and heterogeneous because of the difference in computational performance, which will require load balancing. We will use Xeon and Xeon Phi as compute devices, partitioning the dataset between them. As an example, let's consider a Monte Carlo simulation for Asian option pricing. Fundamentally, this simulation models drift with diffusion in the space of asset price. We have a number of parameter sets that determine drift and diffusion strengths, and each parameter set determines a financial instrument called an option. And for each dataset, we have to simulate multiple random paths to compute certain statistical properties of this stochastic process. Those properties came down to option payoffs. Without going into details of the mathematical model, we can describe this simulation like this. We're going to run the simulation as a distributed calculation. We'll distribute option parameters across multiple compute devices. Inside of each compute device, we will distribute the multiple random paths across the cores and across the vector lanes in the cores. Finally, we will try to use this code on a heterogeneous cluster with Xeon processors and Xeon Phi coprocessors. The question is, how do we partition work between Xeon and Xeon Phi? One trivial choice is to assign the same amount of work to each MPI process, regardless where it is running on Xeon or on Xeon Phi. It is obvious that, in this case, some processes will be overloaded and some underloaded. Xeon Phi may be done with all its work and it will have to idle, waiting for Xeon to finish. In other words, we have load imbalance that can compromise performance. Another option is to introduce a work-sharing parameter, which controls how much more work Xeon Phi should get compared to Xeon. Then, at runtime, we can use the MPI groups functionality to group all processes running on Xeons in one group and all processes running on Xeon Phi coprocessors in another group. After that, each process can compute for itself the subset of the problem that it is responsible for. If the work-sharing parameter is chosen optimally, the application will be load balanced between Xeon and Xeon Phi devices. To choose an optimal value of the load balancing parameters, some calibration runs are usually required. We will run a smaller problem on the target platform with different values of the tuning parameter and find a sweet spot. After that, we will use the optimal tuning parameter in production runs. This approach is called static load balancing. The disadvantage of such a procedure is that first, calibration is specific to each computing system and to each computational kernel. That means that the application is portable only if the end user can calibrate the application for load balance. Another disadvantage is that the code must be aware of the heterogeneous nature of the platform. Yet another option to resolve load balance is dynamic scheduling. With this approach, we do not need any calibration runs. Instead, we designate one MPI process as a boss, which performs scheduling tasks on all other processes called workers. The boss will distribute a part of the total workload between workers, and wait for workers to finish with their work and report back with request for more work. Then the boss assigns more work to the faster workers. Such an application is self-balancing, and it does not need to be aware of the heterogeneous nature of the platform. Disadvantages of the boss worker model are that first, the boss process may occupy too many cores if we want to use the automatic process pinning functionality in MPI. And the second, the scalability of this application may be limited by the throughput of the worker process. To deal with the first issue, we may, instead of giving the boss a whole MPI process, give it just one thread in a process that is also a worker process. To deal with the throughput limitation, we may either implement a hierarchy of boss processes or a collective scheduling algorithm such as work stealing. You can refer to our book and to Lab 4.11 in it for reference implementations of static scheduling and boss worker scheduling. The discussion in the book explains the performance results shown here. Additionally, for information on Asian option pricing and for a case study on heterogeneous computing with homogeneous code, refer to the Colfax research publication at the URL xeon5.com/papers/heterogeneous. This study is also available as a chapter in the first edition of High Performance Parallelism Pearls book. Visit lotsofcourse.com for more information. Once again, if you have any questions, leave them in the comment section below the video. Thank you for tuning in, and I hope to see you in the next episode.